We are Team 3, and today we're going to talk about our final project for 3210 titled Rusty Crystal. My name is Daniel, and I'm here presenting with Mark. So, to remind everyone what our project was, we are creating a driver for the HD44780U base displays. The driver is coded in Rust and is supported by the Rust OS created by everyone in class. As a whole, it is meant to provide additional functionality and practicality for Rust OS by giving an alternative option in terms of display for a more portable operating system.
Now we will run our shell on the LCD display and you can see it in action. Beyond just printing, we have implemented other parts of the display spec. For example, we can set the cursor on.
For the hardware setup used in this project, it is essentially composed of just three main components. If you look on the top right hand side of the screen, it's just the LED screen, Raspberry Pi, and potentiometer. In terms of wiring, the entire LCD module is powered by Raspberry Pi, where the potentiometer then controls the contrast of the display. Other signals are also wired to the Raspberry Pi, like the pulse enable, the register select, which allows us to choose between the data and instruction register, the data lines, and the read and write line, which allows us to read or write from the aforementioned registers. An important thing to note is the 4-bit operation for our setup. The LCD display supports both 4-bit as well as 8-bit operation, with the main difference aside from the extra wiring is that the data must be sent and received twice instead of a single time. When interacting with the display, aside from the instruction and data registers, which are part of the module's hardware, there are two main interfaces at play when programming the LCD. The DD-RAM, or Data Display Data RAM, and the CG-RAM CG-ROM, which is the character generator RAM and ROM. The CG RAM and ROM essentially stores a set of characters and sends character data to the current DD-RAM address based on the signal sent to it, as you can see in this image. The DD-RAM of the module is used for multiple functions, as well as storing all the possible address locations for the LCD display. Our display's size is 20 by 4, and as you can see with this image, the addresses aren't exactly lined up. The first row is linked to the third row, and there's a gap of addresses before the second and last line. The gaps and extra capacity are used to store additional configurations for the display, such as the number of lines, the bit configuration mentioned earlier, as well as the entry mode and cursor or display shift, which essentially determines how characters are written to the screen. The Raspberry Pi communicates with the display through 6 different signals as shown below. However, there are a couple of constraints to take into account when programming, one of which is managing the address space of the DD-RAM so that everything displays at the correct location. Another is the timing of sending each of the signals. Certain operations take much longer than others. Erasing a single character takes a few microseconds of operations, while clearing the entire screen takes a couple of milliseconds. The example below shows how we're able to display a single character H to display using data lines, register select, and the read and write line.
We evaluated several options in terms of how to incorporate the LCD display code into Rust OS. One approach would be to structure it as a flexible library. This way, the display would be configured by the user, and it would even be possible to make it hardware agnostic by providing a simple interface for hardware-specific functionality that can be implemented by the user. This is the approach used by most public libraries. On the other hand, we have a monolithic approach, where the user relies on the OS to handle all interactions with the display. The main advantage of this approach is the fact that it requires no work from the user. They can just use the API out of the box knowing that everything will work. Another important consideration is that it allows multiple concurrent programs to use the display, with their accesses synced by the OS. Ultimately, we had to remember that this is an OS class, so we choose the approach detailed on the right. Let's examine how our LCD display driver fits into Rust OS and enables console output. In user space, we exposed a nice high-level API the user programs can take advantage of. In kernel space, we mirror the design that we use in Lab 2 to implement the console. Specifically, we have a global singleton LCD console, which is implemented with dynamically checked borrow rules. However, while in Lab 2 we used a homemade mutex, here we choose to use a ref cell, which is a part of the Rust standard library. To actually print to the display, the kernel mutably borrows an LCD display object, which keeps track of the state of the display and implements all of the low-level features. Let's see in more detail what steps would be taken when a user process outputs to the LCD console. First, the user program will invoke LCD print, which is a part of the OS API. The supplied argument is a string slice, which can be decomposed into a pointer and length, exactly what is done and saved into registers. A system call is then made. Control is transferred to the kernel from EL0 to EL1. Now we go through several handlers delegating to each other. And finally, we arrive at the destination. We recover the text that the program wants to print from the pointer and length, mutably borrow the LCD display object, and write to it. In reality, we have to check if the LCD display is available, meaning not used by some other program. If it is, we have to wait and only then borrow it. After the output is printed to the display, we can return to the main program. This concludes our presentation. Have a great day.